Well, good morning, everyone. This is going to be our introduction to Calc 2. A little bit about myself. As you know, my name is Donald Robertson, and if you think I've got an accent, what you're hearing is Scottish. Most of you haven't heard me before. I know that a couple of you have, so I speak a little bit differently, but not much. I say Z instead of Z, and I say J instead of J, but it was my alphabet before it was yours, so I'm right and you're wrong. So we got that. I don't tend to use many words that are different. Occasionally I'll say wee when I mean small. It's a wee thing over there, kind of thing. But for the most part, after a few days, most people don't even notice it. It's just a funny way I talk and it works well. So let's get started on our introduction to Calc 2. I guess the first question that probably would come to your mind is, what on earth is Calc 2 going to be about? Well, Calc 1 was about differentiation, really. How do you find the derivative of a function? So you have a function like y equals f of x, and you find its derivative, f dashed of x. And Calc 1 was about all the different techniques that we use to find derivatives. That was the first part of it. So we had product rule and quotient rule and chain rule and logarithmic differentiation and implicit differentiation, all that good stuff. And once we figured out how to differentiate, the second part of Calc 1 was, well, what can you do with this thing called a derivative? And we found out that you can use it to find the slopes of tangent lines to curves, but you can also use it to find velocity, acceleration, rate of change. You can use it to find the tops of hills or the bottoms of valleys, right? Local max and mins, optimizations, things like that. So quite a lot of things you can do with derivatives. So you might say, well, back to my original question, what on earth is Calc 2? Well, Calc 2 is about finding antiderivatives, which we will call integrals. And that's going to be the first part of what we do. We are going to find different techniques for finding the antiderivative of a function, which is typically written using that notation. And we will find, just like we did in Calc 1, methods, tricks that'll allow us to do that. So we will use power rule. We'll end up using things called U-subs, integration by parts, a whole load of techniques. And then after we know or find out how to find these integrals, the second part of Calc 2 is, well, what can you do with them? And the answer is quite a lot. You'll be able to use antiderivatives, for instance, as you'll find out, to find the area under curves and the area between two curves and volumes of rotated shapes and distance traveled by moving objects and work done in lifting things off the ground and throwing them in the air, and who knows what else. You can use integrals in lots of practical ways, and that will be essentially the second half, right? So where do we start? Well, in Calc 1, didn't we start with a problem called the tangent line problem, which was, how do you find the slope of a curve at a given point, right? The exact value for it, the tangent line slope. And from that small, humble beginning, we generated derivatives. And from there, the ball kept rolling. Well, Integration is going to start from a very simple numerical problem that we're then going to expand eventually into an algebra problem. I want you to imagine that we have a curve. Nothing too difficult here. And this curve is called y equals f of x. And it starts at this guy called A, and it finishes at this value of x called B. And the area that we're wanting to find is called the area under the curve. It's essentially that area. And eventually, that is going to generate antiderivatives integrals. Doesn't look like it. But then again, didn't the slope of a tangent line not look like it was going to generate derivatives, right? It looked like it was just going to get you a number, and that was nice, but what could you do with just one number? Well, we'll be able to generalize that. So let's look at numerical ways to find the area under a curve. And that's what we're going to start with. So I'm going to put in a real curve with real values so that this becomes a proper question, if you like. So I'm going to pick one of the simplest functions in the world, x squared. And that's going to be 0. That's going to be 4. So it's going to go 1, 2, 3, 4. And I want to find the area from 0 to 4. And we have a nice little notation for that. We use that symbol. Don't know if you've seen it before, but it basically is the area under the curve from x equals 0 to x equals 4 of whatever the function is, dx. And that's just part of the notation. In this particular example, it's going to be that one, right? So we're going to try and find an estimate for the area of this. And the way that they approach the problem is kind of the way an engineer might do it. I don't really care how I get the answer. I just want a practical way of getting an estimate for the answer. So he might, or she might, split the shape into 1, 2, 3, 4 strips. And we typically use the letter n to represent how many strips. And for each one of those strips, I'm going to find a rectangle, and I'm going to use that rectangle as my estimate for the area. So in this particular question, I'm going to use that rectangle, that rectangle, that rectangle, and that rectangle. Now, if I find the area of those 4 rectangles, would you agree that would be an estimate for the true area under that curve? Would you also agree that it would be bigger than the real answer? So we would say it was an overestimate. Agreed? The area of these 4 rectangles added up would be more than the area under this blue curve. Let's find out what the area of each of these rectangles is. Well, at that point there, isn't the function 1? At this point here, it's 4. At this point here, it's 9. And although I'm not doing this to scale, would you agree at this point here is 16? So this rectangle, so let's see what the area looks like, is 1 times 1. The second rectangle is 1 times 4. The third rectangle is 1 times 9. And the last rectangle is 1 times 16. And if I put these together, I get 1 add 4, add 9, add 16. And I believe I get the answer 30. And I'm going to put, to remind myself, that this is what we call an overestimate. right? It's bigger than the answer I want. Now hold that thought. And I'm going to do the same picture a second time, or at least I'll try. And here's 0. Here's 4. There's 1. There's 2. There's 3. There's 4. Probably not that to scale, but too late now. And I'm going to do a slightly different take on this. See this last rectangle? This strip here. I decided to use the right-hand side to get the height. Couldn't I have used the left-hand side to get the height? And if I did that, wouldn't my rectangle be this guy? Now, if I take this strip, I could have used that point for the height of that one, but I'm going to use the left-hand side value, so that's the height. For this one, it's going to be that one or that one. I'm going to use this guy. And for this last one, I could have used 0 or 1, and I'm actually going to use that side, which basically means that there's not really any rectangle there, it's 0. So let's see what that fellow looks like. Well, the integral from 0 to 4 of this function, which in this case is 0 to 4 of x squared. Oops, dx. Let's see what the area looks like. 1 times nothing. 1 times, well, that height is 1. That height is, when x is 2, this height is 3. And I'm putting this one in, even although I'm not going to use this, the last one is 16. So the second rectangle is 1 times 1. The next rectangle is 1 times 4. And the last rectangle is 1 times 9. And I get 14.
I have a question.
Yes.
How are the overestimated triangles and the underestimated triangles about the same size?
Well, they are, except, do you notice that in this side, you get 4 rectangles?
Yeah.
And this side, you get 4. But aren't they different 4? Isn't this like 4 to the left and 4 to the right? So although the rectangles are the same, they're not using the same rectangles. Isn't this one just using these 3 and a nothing, and this one is using these 4? Is that okay?
Oh, yeah, I see. Thank you.
Right. Now, what do I know about this? Well, don't I know that this is what we call an underestimate? Would you agree that all these rectangles, don't they add up to something that's less than the area under the curve? Now, if you put those two together, then I should be able to say that the exact area, right, the true area under this curve is somewhere between 30 and 14. Would that seem a reasonable assumption based on the shape of this curve and the way in which I estimated? Now, how could I get a better estimate? Because right now, all I can tell you is that the real answer is somewhere between 14 and 30.
Wouldn't you have to have more rectangles in order to get it more accurate?
Yeah. So can I do 400 strips? Not that I will, because that would take forever. But can you imagine a computer program could do that for you, right? Can I do 400 strips? And what will be the net effect is that if you imagine this is what the range looks like when you did 4 strips, and I'm making this up because I don't have the time to do it really, but imagine I did 400 strips. Couldn't we answer look something like this? Can you imagine that's the kind of result that you would get?
Yeah.
And so if you wanted to, couldn't you find the exact area under that curve to any accuracy that you wanted just by doing enough strips? Like 4 billion strips, 4 trillion strips, American debt strips, right? Whatever you liked. The more strips you do, won't the two answers come together to the point where they're almost indistinguishable from each other? It's a kind of limiting process in a way, isn't it? But the limit is, as the number of strips goes infinite, you should be able to get the answer to the exact area under a curve. And that's what we're trying to figure out here. How to find a method, a numerical method, to find the exact area under the curve. And these two are the ways that we're going to start that process. They have some names, which I haven't given you, so now I'll give you them. On this one here, do you notice that we could choose the left or the right-hand side to get the height of the rectangle? But we always choose the right-hand side in each pair, right? So in this last one, we could do it 3 or 4, but we chose to use 4. This is called R4. R, you use the right-hand side, right? You've got a strip and you can either use the left or the right, but you use the right-hand side, okay? And you use 4 strips. What do you think this thing's going to be called?
L4.
Yeah. So if you have a curve and you do 5 strips, so you break it into 5 equally width strips, and for each strip, you always choose the right-hand side to get the height of your rectangle, then you're doing an R5. If you do the left-hand side, you're going to do an L5. Are we comfortable with that notation, left and right? L5, R5. Right. If I said L500 or R500, you wouldn't like me because it would take you a day to do that by hand, agreed? But you're never going to be asked to do ridiculous numbers, right? In the homework questions, it's 8 strips or something. Now, it's still going to be, and there's no arguing about this, it's going to be laborious, right? It's not going to be algebra and clean. It's going to be messy and numerical, right? With lots of things that you just have to keep track of. So I'm going to do an example of that process and show you some of the ways in which you can set it up to just make your life a little bit easier, right? So to be able to do that, I need to kind of set up a little bit of the general process so that we can use that for every question. So I want you to imagine now that we have any old function in the world, y equals f of x, and it starts at x equals a, and it finishes at x equals b. So your question might be to find the area under the curve from a to b of this function. So that's what your goal is. I want you to imagine that you took this and you split it into n strips. The first thing we're going to find is the width of one strip. So imagine you're taking it and you broke it into 5 strips or 25 strips. How could we come up with what one width would be, right? If you take the start and the finish and you divide it by how many strips there are, that is going to be the width of one strip. So over here, I'm going to show you how that would work in a real question. So let's suppose we have, let me think of a nice one. If you hold on a second, I'm just going to create a function. Looks good. Can you just trust me that that's what x squared minus 3x squared plus 2x looks like from 0 to 1, right? The rest of it curves around and goes up like that, and the side goes down like that. Right, so there's my function. Right, now, I don't want to make my life too difficult, so I'm going to do 5 strips. Right, the width of one strip, which is called delta x, and typically every textbook you're going to see, is b take away a over n. 1, because that's basically b, take away 0, which is a, divided by 5. That is 0.2. Whoops. So far, so good. Now, we set up a little table. The x coordinate, the value of the function. And I want you to imagine what that might look like in a general sort of a way. Well, the first guy is going to be a, right? And he is called x naught. And then the next one after that is going to be a plus delta x. So can you imagine this fella is a add a delta x, a plus delta x, and then so on and so on. Right, what would that look like is a real question. Well, you go down here. Here's your function. And you're going to start at 0. And you're going to go up in 0.2s. And if you're interested, this is called x0, x1, x2, x3, x4, x5. Now for every single one of these fellas, you find the value of the function. So I'm going to take this function and evaluate it at all these points and write in the answer. Now, let's imagine that we only want the answer to say 3 decimal places, right? Could happen. So I would want to cut my work rate down so I don't have to do this thing 6 different times, although to be honest, that one's easy, right? And that one's easy, right? I can see that they are, right? But I still have to do some of them. Wouldn't it be nice if we could use calculator? So let me show you how we do that. So you go in. I think you've got some like 5 questions if my memory serves me, which it doesn't always do so. You're going to have about 5 questions where you kind of have to do this. And then in the next section, you've got about another 4 questions where you have to do it again. So you're going to have a fair old shot at doing these. Right, so what you got here is a calculator, and I'm going to use it to fill in that table. So I'm going to go and I'm going to go to y equals, and I'm going to type in x cubed, subtract 3x squared, and add 2x. And then up here, it's called table set. So second table setup. And in this case, it starts at 0, which is perfect. And the thing that they're calling delta table is my delta x, and that's 0.2. And that's it, it's set up. So tables start at whatever a is, in this case 0, but maybe in the next question it's 1 to 7, right? So it'll start at 1. And it'll go up in 0.2s in this case. So all I need to do now is hit second and table. And the guys that I need are already written. 0.288, 0.384, 0.336, and 0.192. Now, can you imagine if that function was really ugly or you had to do a lot of them? Wouldn't this save you a little bit of time? Right. Just to get the calculator to take some of the workload off you. So let's return now and see what we do next. So if you were given this question, the first thing you do is find delta x, which is 0.2. That allows you to set up this table. And I am now going to do an L5 and an R5. And you might say, well, how do you calculate? Remember, you've got a strip and you pick the left-hand side all the way along, and then you get the same strip, but you choose the right-hand side and you do it all the way along. How am I going to get the total of these guys? Well, in general, if you want to do an LN, it's delta x, the width, times various heights. But since delta x is the same all the time, you can pull it out as a common factor. And if you're doing the left-hand side, you use the value of the function x0 plus the value of the function f1, and you finish at the second last guy there. And you finish at the value of the function n-1. And if you want to do the right-hand side, it looks almost the same, except you start at fx1, oops, and then you do x2, and you finish at the end. So what does that look like in this case? Well, it's going to be delta x times, I'll just go dot dot, all that stuff. It's 0.2, that's delta x. And when you do L5, you use these 5 numbers. So you basically go 0, 0.288, 0.384, 0.336, and you finish with 0.192. And you're just going to trust me on this. 0.288 plus 0.384 plus 0.336 plus 0.192, and I get 0.2 times 1.2, and the answer I get is 1.44. And give myself some more room here. Have you noticed that if I was doing this strip, can you imagine that would be my 5 strips, right? And all I've done is I've chosen the left-hand side, which are all these guys, including that one. So there's my estimate. And I can choose R5. Well, R5 is basically those 5 numbers. Wait a minute, here's a bit of luck. Isn't this number all of those added up? Isn't this number all of those added up? By sheer luck, isn't this answer the same answer? They're both 0. So won't you end up with 1.44? So in this particular question, the area under this curve is 1.44 in both. And that was just a sheer coincidence. Is this an overestimate or an underestimate, or neither? If you use these 5 rectangles to estimate the area under this curve, would these 5 rectangles be an overestimate or an underestimate, or neither?
I want to say neither.
Correct. Your gut feeling was right. Because aren't some of them, these 3, a little bit less than the real ends, but aren't these 2 a little bit more? So R5 and L5 aren't always going to be over and underestimates, as were my first example. In this case here, they're just 2 different estimates. The fact that they're both equal is a bit of an annoyance. I wish they were different, but they're just a luck of the draw. So when can you get over and under? Well, if your function is always increasing or always decreasing, in those situations, one of them will be an overestimate and the other will be an underestimate. Can you see just by the structure of things that when you choose whatever you decide to choose, in this case I'm using the L one, wouldn't L5 be an underestimate? And if I use the other side, can you see that all of these are bigger than the answer? So if your function is increasing or decreasing, the left and right, L5 and R5, one will be, the big one will be the overestimate and the smaller number will be the underestimate. And if they're going this way, it's also true. The only difference is the right and the left switch places. And you can imagine that. If you were doing the right-hand side, aren't the right-hand side going to generate rectangles that are bigger than the area? When it's an underestimate, aren't the right-hand side going to give you rectangles that are less than the real area? Right? And that's the difference. Okay, any questions about this process? Because trust me, we are going to do quite a few of them before we're finished. Right, it's not algebraically messy, it's fiddly, for want of a better word. Don't you have to find your delta? You need to create this table. You then need to realize that it's going to be whatever delta is, add up all those numbers to get L5, and add up all those numbers to get R5. I'm going to change tack for the little time that we've got left, and going to show you some of the stuff that I think will be helpful. I hope you are looking at, let's go, here we go. This is what your Canvas page should look like. Is that what you're saying right now? I see some nods. Am I showing you a Canvas page right now?
Yeah.
Okay, we're good. Now, this is the bit that you should already be aware of, but the fact that you came to class means that you already know how to do the Zoom stuff. Over here is the syllabus. And when you want to communicate with me, it's a good idea to do it using your college email address. I don't want things getting dumped into the, what's the word? You know, the place where emails disappear to because it's not a college student's email. And we have filters that stop garbage from entering. So if you don't use your college email, that might happen to it. It might go into the rubbish bin. So make sure you do that, please. There's going to be an office there, which is basically just going to be a Zoom meeting like this, so you can just turn up. And I will put that up, the link to it, starting tomorrow, because I didn't think we would have an officer. We haven't even had a class yet. And you can just come to that. When you turn up for the office, it may not let you in. It's a bit like turning up to my office physically and there's somebody in the room. So you may just have to wait there and then I'll let you in, you know, once that person has been dealt with. You can also send me emails if that time doesn't work and we can arrange a Zoom meeting. I can also answer simple emails if you just want to say, look, I'm done question 9 and it says, I say 17.12 and it doesn't agree with me and what's going on. I can answer that. Hopefully you've all got the right prereqs. You need to get a webcam because when we do a test, I'm going to have to see you so that for security reasons. All this is the good stuff. So let's look at what we've got. Things are done in 2-week chunks. That's the way I organise them. So the first 2 weeks, finishing on Friday the 15th, we are going to cover these sections. 5.1 is kind of where we started today. We'll continue that tomorrow. 7.7, I know it's a weird number. That's going to be more numerical techniques. And that will happen this week as well. And then pretty much that's the end of the number crunching. And we get into the good stuff, which is algebra, right? How do you find the exact area under a curve using antiderivatives, essentially? And we'll show you some of the basic techniques and our first trick. Homework for these 2 weeks is due on the Sunday of the 17th. And then on Monday the 18th, we have a test. So you've got until Monday the 18th to get a webcam. If you don't have a webcam and you can't afford one, if you contact the college, they can issue you with one, a loaner, so that you can use it. And the information to do that is in Canvas as well. And then we do 2 more weeks in a test, 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 right? It kind of follows that theme all the way through. And then you have a final. So, pretty clear? Right. I may wiggle like the last one. I might not finish at that quarter that goes here, or I may finish early and I'll bring this one up there. So this isn't written in stone, but for the most part, what you see is what you're going to end up getting. There won't be really any major changes. Now, if I wind back, what else do we have? Well, if we click on this one, this week uses that link for the entire week. So this one here, the one that got you here, is the same link that you can use Tuesday to Friday, same link. When you look at this, you might say, well, what's this all about? Every single lesson, including this one, gets recorded. and I will put it in here. I am asking your permission to do so. Now, if any of you have a problem with me putting this lesson online, feel free to tell me and we won't do it. Now, I'll give you a little proviso. I like to talk to people because I'm nosy or curious. I always cut those bits out. So if I ask things like, that's a cool second name, where does it come from? And you don't want, you know, you don't want that to be shared or whatever, then I won't. I don't do that. So only things that get put onto the Zoom are when the lesson officially starts and then when it officially ends, right? Nothing else appears. If you do an officer, they never appear. I never record those, right? They don't get kept. So you don't need to worry about, you know, people finding out that you don't remember how to differentiate something or whatever. Any questions so far? Okay, let's move on. Yes.
So about the you said recording the Zoom meetings. So I'm located in Germany. So for me, it's about 9:40 something p.m. So for me, it might be a good option to do that or tune into the Zoom meetings at a different time. How often are you going to post where you do daily lecture? Is that going to be a daily lecture? You're going to post daily lectures, or will it be every 2 days?
Hector, there is a participation grade that you do not want to miss, okay, and you only get them by turning up. Okay. So you have to be here at this time. It's kind of nice there in Germany. They do good beer there, so you're lucky in that respect.
Beer is the best.
Yeah. Yeah, I've only been to Germany once. It's a nice place. It's not like a German ever did anything bad.
Yeah, no. Yeah, I'm over by Rhineland. So yeah, yes, if there's gonna be a daily class meeting, yeah, I'll definitely attend to.
Right. Right. But the Zoom are there because not everyone's, I'm included, have got a perfect memory. So sometimes, especially this messy stuff that we've done today, you might want to go back and look at saying, what did he do again? And where did that number come from? So you just go back and look at the Zoom lesson a second time. Now, course assignments, already mentioned them, so I guess that's in syllabus. If you click on this one, this is basically some extra things for you to do. So if you click on this one here, I have got videos that I've got from various places that I found that are useful. And if you want to see how someone else described it, or wanted, you know, some more examples, because we don't have enough time to do, I mean, each one of these questions could last 15 minutes, right? And I don't have enough time in the day to do plenty of examples. So if you click on the video and you do that, you can basically watch someone else do, as you can see, a similar kind of thing to I've done, right? You see all the X, not X1, X2s, and there's that delta X stuff just written in a slightly different way. It's a resource, hopefully, that you can choose to use or not, but it's useful. If you scroll down a little bit further, here is some notes on how you can use your TI-84. Remember that table thing I did? Here's some videos and notes on what I was doing. Here is a PDF, which you probably can't see because of the way it is, but it's just some notes that I put together. Not everyone learns the same way. Some of you are auditory learners, you hear things. Some of you need to see things. Some of you need to write things down. So I've tried to give you as many different forms of that information as I've possibly can. So if one thing doesn't work for you, maybe one of the things that I've done in this resource here might work for you a little bit better. If you kind of look at this one here, because I've just randomly stopped at this page here, what we have here is a very general version of how to find the area under curves. Right? It's a very algebraic thing. This particular piece doesn't happen until later on in 7.7, I think. I think it's 7.7 it helps. Any questions? Are we good? Here's some homework help. Can't say I don't give you stuff. And it's basically just some more algebraic versions of some of the questions.
Sorry.
Yes.
For the homework, the WebAssign homework, so each section's homework, they're all going to be due on January 17th?
Yeah. Although I strongly suggest that you don't wait until January the 16th to do them all. So start doing them pretty much even after today. You should at least be able to do some of the earlier questions because they're really just, you know, put together. Well, I'm at it, so let me show you what that looks like. I'll just go into student view. So, oops, no, we won't. Excuse me. I forgot one step. There we go. Okay, so this is what your WebAssign page would look like. This is what you see, right? And if I click on 5.1, for example, eventually, here is a table. So they've already basically given you all the X0, X1s, X2s. And they're asking you to find the smaller and the larger one. So can you imagine in this case here, what would the delta X be? I guess you should call it delta T because the variable's T. What is the width of each rectangle going to be based from this table?
0.5.
0.5. Now, aren't you going to then do, I'll cover this, I can't, right. There, I put my mouse over it. Do you see those guys there on the left-hand side? See if you add them all up and multiply by 0.5, won't that be your L5? Right, your left 5. And if you add up all those guys, and I'm talking about these red numbers, if you add all them up and multiply it by the width, which is 0.5 again, wouldn't that be the guy we call R5? Now, they haven't said, tell me L5 and R5, but because of the way the table's constructed, I know that's what they want. Now, one of those numbers is going to be 82 and the other one's going to be 62. Made that up, right? But that's what you're going to get. If that was the case, won't 62 go in here and won't 82 go in there? Can you tell that I know that because isn't this table increasing? So if you plotted that, wouldn't this be an increasing function? And when it's an increasing function, doesn't the L and the R give you an upper and a lower estimate, right? So the two answers, the biggest one goes here and the smaller one goes there. Can you see this question is a similar idea? Only this time, if you cover that one up, 1, 2, 3, 4, 5, 6, you'll get to one end, and if you cover the other one up, you get the other. This one here, jumping ahead too far, right? Anyway, there's your homework. As you do it, you get 3 shots. At the end of 3, it's over. If you get it right, it tells you you're right, and you just move on. You have to be careful about accuracy in some of the questions. If it doesn't mention the accuracy, then you should be okay just to write down what you've got. But if it wants the answer to 2 decimal places, well, you make sure to round off your final answer to 2 decimal places. and not 4 or whatever it might be. Right, any more questions? You got a lot to take in. So before we go, a few last tidying up things. First thing is we take participation. So if you can go down to the chat place and say hi, that's how I will register you as being in class today. I just look at your name. If there's a hi next to it, I know you were here.
I also had a question about the exams if we have a little time.
Sure, go for it.
So how, I know from previous math classes, they've had us upload it like through email or like through a PDF. How
Right.
are we going to do that since we're going to be doing it on a webcam?
Ah, right. Let's show you how this is going to work. Good question.
Awesome. Thank you.
Test, yeah. 2 weeks from now, right? 2 weeks from today, in fact, you're going to get your first test. It will be in WebAssign, just like a homework, but it won't be available until 1 second past 1. And you will have exactly 50 minutes in which to finish it. That's not all. I will be watching you through the webcam. You make sure your big sister's not over your shoulder telling you how to do it. So that's one reason that I need to see the webcam, right? Once you've finished it, the next bit, and we'll talk more about this closer to the time, I want to see your working. Now, there are 2 reasons. The first one is security. If you just copied the answers because somebody gave you a list of them, right? That would be pretty obvious because I won't see any working. The second thing is more important than that. You get a lot of partial credit from working. WebAssign, in normal homework, it ain't a big deal because you get 3 shots. If you get it wrong, it tells you you're wrong, you get another shot. In the test, you only get 1 shot. And it doesn't tell you if you're right or wrong. It tells me that you're right or wrong, but it doesn't tell you. So if I see you're working and you put in 14.1 and the right answer was 14.2, WebAssign is going to give you 0 points because it's wrong. But I will look at it and say, yeah, she done that table, she added those numbers up. Oh God, she multiplied by 0.4 when she really should have done 0.5. Okay, she loses a couple of points, but she's not losing all 20. So that's the main reason I want that. Now you might say, well, how do you get all that working to me? That's the tricky part. I've got a program, a free one called Adobe Scan, and there's a link to it. And basically you take your phone and you take pictures of it, and it turns it into a PDF, and you upload it into Canvas. So if you've ever uploaded an English project, it'll be very similar. And then I look at that, and that's where I give you your extra credit. So that when you get your test 1 back, WebAssign might say you get 15 out of 20. But it ends up being 80 out of 20 when I go and look at it. Because this stuff here is notoriously messy. Can you imagine you just write 11.23 and it was 11.32? I mean, it's so easy to do. And I'm not going to penalise you a heck because they're a little careless. That's all it takes. You get 0 because WebAssign isn't resilient. Good question. Any other questions?
Oh, just about the same thing. In your previous classes, you had us use Cam Scanner for this. Is the Adobe one just better, or will
It's
Cam
free.
Scanner work too?
Cam Scanner was free, and then they started charging you. But Adobe Scan is free all the time, so I'm doing it to save you money. But if you've got Cam Scanner and you've managed to buy it, feel free to use it. I think some other people might have got other software that's done it because their English class told you about this other thing that you could use. But I doubt it, because in English, don't you probably do it in Word and then convert it into a PDF? Yeah. So Cam Scan is fine, but Adobe Scan is free, and it does exactly the same job. So it shouldn't take you too long to figure it out. You just take a picture and boom, hopefully.
Weird. How recently have they started making you pay for it? Because I used it as early as like last semester, and they still haven't.
I don't
But any
know, but
payments?
I've been told by students that they're asking them to pay, so I'm only
Okay.
going by what they tell me.
Okay.
I
Well,
mean,
thank
if
you.
it's still free, keep using it. If you like it and you know how to use it, don't change it because I told you to. It's because all
Okay.
you get is a PDF. I don't know where it came from. You know what software used it. And some of you might have a scanner in your printer. Can't you just stick it in your scanner and PDF it that way? That works too. I mean, well, you know, I don't. You know, you've all got different technology or lack of. So whatever works is fine. As long as it ends up as a PDF and it goes into Canvas, we're cool.